So here are two questions from static equilibrium. The first one is not that difficult, but the second one is really a very interesting question. So the first question talks about a horizontal uniform strut weighs 400 Newton. One end of the strut is attached to a hinged support at the wall. So you see that it's hinged here, it's supported at the wall. And the other end of the strut is attached to a sign, so that's a sign, that weighs 200 Newton. Okay, so that's 200 Newton. The strut weighs 400, so that's a strut, and the sign weighs 200 Newton. The strut is also supported by a cable, so the cable, attached between the end of the strut and the wall. Assuming that the entire weight of the sign is attached at the very end of the strut. So that's an assumption. So we got to assume that the entire weight of the strut is acting through one end. Usually it would be through the center of gravity, but in this case, we have to assume that its weight is entirely acting through one end of the sign. So assuming that the entire weight of the sign is attached at the very end of the strut, find the tension in the cable and the force at the hinge of the strut. So that is the question. We got to find the tension in the cable and the force at the hinge. Now remember that we don't even know the direction of the force at the hinge. So we got to just assume that it's in a particular direction, maybe like this. So we do not know the angle that the force makes. All right, so let's do this. In order to do this, we have to use the two conditions for static equilibrium. Namely, number one, if you take the total torque at any point, it should add up to zero, which means the clockwise torques must sum up and be equal to the counterclockwise. So clockwise torque about any point must be equal to the counterclockwise torque about the same point. That's the first condition. And the second condition is that the total up forces should be equal to the total down forces. That's along the y-axis. And again, the net forces along the x-axis must also be zero, which means the forces to the right must be equal to the forces to the left. So total cancellation of forces both along the y-axis and the x-axis. Those are the two conditions. So here are the forces acting. You see, that what I've drawn here is the 400 Newton, which is the weight of the strut, because it will act right through the center of gravity, which is the center. So that's 400 Newton. And then you have the tension in the cable shown here. And also you have the weight of the sign, which is 200 Newton acting here. And then what I did is I resolved the tension into its two components. So the tension is resolved into the y component and the x component. So this angle is given as 30 degrees. Therefore, this component is going to be t cosine 30, because that's the adjacent side of the triangle that's formed here. So that's t cosine 30, and this is going to be t sine 30. That is the force. We don't even know the angle that the force makes, but it doesn't matter. You know why? Because we're going to apply the condition for torque being equal to zero, and we're going to calculate the torque about this point. Since the force F is acting at that point, the distance is zero. Therefore, the torque due to this force will be zero. It doesn't matter what angle it acts in, because the distance of the force from that point is zero. So the torque is zero due to that force. But when you look at the other forces, you see that the 200 Newton and the 400 Newton are trying to turn it clockwise. See, trying to turn it clockwise. While the t sine theta is trying to turn it counterclockwise. What about the t cosine theta? See, the t cosine theta is acting along the line where we were calculating the torque. You see that? So there is no distance. There is no perpendicular distance. So because that is going to hit that point, there is no perpendicular distance. So if it was right here, then this would have been the perpendicular distance. See? But it's right here. So there is no perpendicular distance for t cosine theta. That means there are two clockwise torques, namely the one by 400 and the other by 200. And there is one counterclockwise torque, which is t sine 30. So now we're going to say t sine 30 times the distance, and this distance. So we have t sine 30 multiplied by 2. I'm just taking this as 2 meters. Okay, the length is not given, but we know that if we take this as 2 meters, then this is going to be 1 meter because it's exactly at the midpoint. So you can take it as 2 and 1 or 4 and 2, it doesn't matter. So I'm taking that as 2 meters. So t sine 30 multiplied by 2 is equal to 400 multiplied by 1 plus 200 multiplied by 2. You see, all distances are measured from the hinge because that's where we're calculating the torque. So when you do the math, that's going to give you 800 newtons. The reason is sine 30 is half, and then half multiplied by 2 just cancels out. And then on this side you have 800. So we got the tension as 800 newtons. Now we got to find the force at the strut. That is when we look at this force F and then we break it into its components. So we're going to get the X component and the Y component. Okay, so here it is. Fx is going to be t cosine 30. Why? Why is Fx is equal to t cosine 30? Because you see that the total force along the x-axis must be 0. We only have one force along the x-axis to the left, which is t cosine 30, and the other one is Fx. So they must be equal to each other, so they cancel out. That's why Fx is t cosine 30, which is, because t is 800, 800 cosine 30, which gives 693 newtons. What about Fy? All right, Fy plus t sine 30, both of them are up, should be equal to 400 plus 200. Fy plus t sine 30, total up, is equal to the total down. So Fy plus t sine 30 is 600. That means Fy plus t is 800. So 800 times sine 30 is 600. And then when we do the math, we will get the value of Fy. Now sine 30 is half, so 800 times half is 400. And that gives Fy as 200. Since we know Fx and Fy, now we can find the value of F simply by taking the square root of the sum of the squares. So that's Fx squared plus Fy squared, square root of that. And that gives 693 squared plus 200 squared, and we get it as 721 newtons. That is the value of the force at the hinge. So here is the second question. And this question, we really need to do it carefully. So a uniform trapdoor shown below is 1.0 meter by 1.5 meter and weighs 300 newton. So the dimensions are 1 meter and 1.5, and the weight of this because it's uniform, see that word there, that means its weight is going to act through its center. So the weight is going to act right through the center, vertically down, which is 300 Newton, okay? And it's supported by a single hinge, see the hinge there, single hinge, and by a light rope. So the yellow thing is the light rope tied between the middle of the door and the floor. So that's the rope. And the angle that the rope makes with the floor is 20 degrees. But the angle made by the door with the floor is 30 degrees. And then we got to find the tension in the rope and the force at the hinge. We got to find the tension in the rope and the force at the hinge. So the diagram is once again very important in this case. So let's do it. So these are the forces. So 300 Newton is the weight of the door. And then you see the tension acting down is broken up into its x component and y component. So that is what is shown there. So t cosine of 20 and t sine of 20, because the angle is given as 20. Well, I'm drawing it again because there could be some confusion. So that's the hinge. That shows the components now, t cosine 20 and t sine 20. But remember that this angle is 30 degrees and this distance is 0.75 meter. The triangle is ABC. Okay. So let me just remove that for a second. So how is it 0.75? Because the total is 1.5. That means this part, which is half of 1.5, would be 0.75. So you see, I'm actually drawing this triangle here. And then I want to show you how it's different from the other triangle. See, that's the 20 degrees. So you can now see that this is the string, and the string is making 20 degrees with the floor. So I hope that's clear. This is the trap door. Okay, it's half of that, so 0.75, the angle. So if the figure is clear, then it's easier to understand. So what is AB? Just from the triangle, from this right angle triangle, AB is the opposite side, so it's going to be 0.75 sine 30. Okay? Which is 0.375. And similarly, BC, the side is the adjacent, so it'll be 0.75 cosine 30. And that is 0.6495 meter. So once you get that, we're going to calculate the torque. And remember, we can calculate the torque about any point, but I'm going to calculate the torque about the hinge. Okay, so about the hinge. That means all perpendicular distances have to be measured from the hinge. So number one, you see that t sine 20 is trying to turn it counterclockwise. The 300 Newton is also trying to turn it counterclockwise because they're along the same line. You can see t sine 20 and 300 both are trying to turn it counterclockwise. But t cosine 20 is trying to turn it clockwise. Is that clear? And what is the distance of t sine 20 and 300 from the hinge? Wouldn't it be BC? Because this is where you have t sine 20 and 300, and the hinge is here. So the perpendicular distance is BC. We always take the perpendicular distance between the force and the point, okay? So that is the perpendicular distance. But when you take the torque due to T cosine 20, that is the force, and we need the torque here. So isn't this going to be the perpendicular distance? Yes, which is the same as AB. So that will be T cosine 20 times AB, which is 0.375. So again, on the left-hand side, I have the total counterclockwise torque. On the right side, I have the total clockwise torque. They must be equal to each other. And then we plug in the value of sine 20, which is 0.342. And then that is 0.6495. Here it's the value of cosine 20. And then we have to collect the t terms together and calculate the value of tension. So you may have noticed that the most important point is to take the distances. If you have the force this way and the point is here, you always go for the perpendicular distance between the line of action of the force and the point. So that's where you have to be careful. And when you do all the math, you would get the tension as 1,498 newtons. If you look at sig figures, it's going to be 1,500 newtons because the weight is given as 300 newtons, so there's only 3 sig figures. So it's 1,500 newtons. All right, next, we got to find what? We have to find the force at the hinge, which I've not even shown up to now. So let's do that. So here is the diagram again. So that's the hinge. So T cosine 20 and T sine 20. I'm just drawing that again. Can move that along. And yeah, we come to the important part. So now you can see that the red arrow shows the force at the hinge. So again, we don't know the angle that that force makes with the floor. So I've just drawn it like that and broken that into its y component and the x component. I'm assuming that this angle is theta. Okay, we don't know what it is. And I'm just going to call the vertical Fy and the horizontal Fx. So that is the complete diagram now. And when you look at the forces, we know that the total up force should be equal to the total down force. So we have Fy as one of the up forces, and then there are 2 down forces. Those are T sine 20 and 300. So Fy should be equal to the sum of T sine 20 and 300. Similarly, if you look at the forces along the x-axis, you have Fx to the left, you have T cosine 20 to the right. So they must be equal to each other. And then you substitute the value of T because we have it as 1498, sine 20 plus 300, and that gives 512.34. Do the same here, 1498 times cosine 20, and we get the value of f sub x as 1407. So since we have fx and fy, we can find the value of f by taking the square root of the sum of their squares. So that would be square root of 1407.66 squared plus 512.34 squared. Right, and I think I made a mistake in the calculation there. Oh, I've corrected it now. When I wrote it as 5, but it's actually 812, so I had to change that. So it's 812.35. And then when you do this, you get 1625 newtons, which is about 1600 newtons, considering the significant figures. And then we can also find the angle by using tan theta is Fy by Fx. That gives tan theta is equal to 812.35 divided by 1407.66, and that gives 0.577. Take the arctan of that, or the tan inverse, and you get theta as 30 degrees. So that's how we do these problems. Now, both the problems are good, but the second one is especially very important, and I hope you understood how I worked out both the problems. All right? Very good. Take care. We'll see you on the next video.